Introduction to TURN and STUN. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving deep into one of the most critical components of real-time communication on the internet: TURN and STUN protocols. These protocols are the unsung heroes that make video conferencing, voice calls, and peer-to-peer communication possible across the modern internet. Without these technologies, applications like Zoom, Microsoft Teams, WebRTC-based applications, and countless other real-time communication tools would simply fail when users are behind NAT devices or firewalls, which is the reality for the vast majority of internet users today. STUN stands for Session Traversal Utilities for NAT. It is a protocol designed to help clients discover their public IP address and the type of NAT they are behind. This information is crucial because most devices today sit behind routers that perform network address translation. When you are at home or in an office, your device has a private IP address like 192.168.1.100, but to communicate with the outside world, your router translates this to a public IP address. STUN helps your application understand how this translation works so it can establish direct connections with other peers. TURN stands for Traversal Using Relays around NAT. While STUN helps establish direct connections, TURN comes into play when direct connections are impossible. Some firewalls are so restrictive, or NAT configurations so complex, that even with STUN's help, two peers cannot connect directly. In these cases, TURN acts as a relay server, forwarding traffic between the two peers. Think of it like a post office. If you can't hand a letter directly to someone, you give it to the post office, and they deliver it for you. These protocols work together in a complementary fashion. A typical real-time communication application will first attempt to use STUN to establish a direct peer-to-peer connection. This is the most efficient approach because it minimizes latency and does not consume server resources. However, if STUN fails, the application falls back to TURN, which guarantees connectivity at the cost of higher latency and server resource usage. This fallback mechanism ensures that connections can always be established, regardless of network topology. Understanding NAT and its challenges. To truly appreciate why TURN and STUN exist, we need to understand the problem they solve: network address translation, or NAT. NAT was originally developed as a solution to IPv4 address exhaustion. With only about 4.3 billion IPv4 addresses available, and billions of devices needing internet connectivity, it became clear that we couldn't give every device a unique public IP address. NAT allows multiple devices to share a single public IP address, which is how your entire home network can operate with just one public IP from your internet service provider. Here is how NAT works in practice. Your device has a private IP address, for example, 192.168.1.100, and it wants to communicate with a web server at 203.0.113.50. When your device sends a packet, it originates from 192.168.1.100 port 54321 to 203.0.113.50 port 443. However, when this packet reaches your router, the router performs address translation. It replaces your private source address with its public IP address, for example, 198.51.100.10. and maps your source port 54321 to a different external port, perhaps 62000. The router maintains a translation table that remembers this mapping. Internal address 192.168.1.100:54321 maps to external address 198.51.100.10:62000. When the web server responds, it sends packets to 198.51.100.10, port 62000. Your router receives these packets, looks up port 62000 in its translation table, sees that it maps to 192.168.1.100, port 54321, and forwards the packet to your device. This works perfectly for client-server communication where your device initiates the connection. The problem arises with peer-to-peer communication, where both devices might be behind NAT, and neither can initiate a direct connection to the other. There are different types of NAT behavior, and they vary in how restrictive they are. Full cone NAT is the most permissive. Once an internal address is mapped to an external port, any external host can send packets to that external port, and they will be forwarded to the internal address. Restricted cone NAT adds a constraint. External hosts can only send packets if the internal host has previously sent a packet to that external host's IP address. Port-restricted cone NAT goes further. The internal host must have sent a packet to that specific external IP and port combination. Finally, symmetric NAT is the most restrictive. Each new destination gets a different external port mapping, making it nearly impossible to predict what external port will be used. The type of NAT matters enormously for peer-to-peer connectivity. With full cone NAT, it's relatively easy to establish direct connections. With symmetric NAT, it's often impossible without a relay. STUN helps applications discover what type of NAT they're behind and what their public IP address and port mapping are. TURN provides the relay fallback for cases where direct connection is impossible. Together, they provide a comprehensive solution to NAT Traversal. STUN Protocol Architecture. The STUN protocol operates on a simple yet elegant client-server model. A STUN client, which is typically embedded in your real-time communication application, sends a request to a STUN server located on the public Internet. The STUN server examines the incoming packet and extracts crucial information from it, specifically the source IP address and source port as seen from the server's perspective. This is the public IP and port that the rest of the Internet sees when your device communicates. The beauty of STUN lies in its simplicity. The STUN server does not need to maintain any state about clients. It simply responds to each request with information about what it observed in the incoming packet. The response contains the reflexive transport address, which is the public IP address and port combination that the STUN server saw. This tells the client how it appears to the outside world after NAT translation has occurred. STUN messages follow a specific format defined in RFC 5389. Every STUN message begins with a 20-byte header. This header includes the message type, message length, a magic cookie used for identifying STUN messages, and a 96-bit transaction ID. This ID helps in matching requests with their corresponding responses. Following the header are 0 or more attributes, which are type length value encoded. The most important attribute in a STUN response is the XOR mapped address attribute, which contains the client's reflexive address. The XOR operation in XOR mapped address serves a specific purpose. By XORing the IP address and port with the magic cookie and transaction ID, STUN prevents NAT devices along the path from accidentally modifying these values. Some older NAT implementations perform deep packet inspection and modify IP addresses they find in packet payloads, which would corrupt the STUN response if the address weren't obscured by XOR. This XOR encoding ensures the address arrives intact at the client. STUN also provides mechanisms for NAT behavior discovery. By making multiple STUN requests from the same local port to different STUN servers, and comparing the reflexive addresses received, a client can determine what type of NAT it is behind. If the reflexive address is always the same, it is likely a cone NAT. If the reflexive address changes with each different destination, it is symmetric NAT. This information helps the application decide whether direct peer-to-peer connectivity is feasible or whether it needs to fall back to turn. STUN message exchange flow. Let's walk through a detailed STUN transaction to see exactly how the protocol operates in practice. The process begins when a client application needs to discover its public IP address and port mapping. The application creates an STUN binding request message, which is the most common type of STUN message. This request is sent over a UDP to an STUN server, typically on port 3478, though STUN can also operate over TCP or TLS for scenarios where a UDP is blocked. The client sends this request from its local IP address and port. For example, 192.168.1.100, port 54321. As the packet traverses the network and passes through the NAT device, the source address gets translated. If the NAT is performing port-restricted cone NAT, it might map this to 198.51.100.10, port 62000. The STUN server, which has a public IP address like 203.0.113.5, receives the packet. From the server's perspective, the packet originated from 198.51.100.10, port 62000, even though the client thinks it sent from 192.168.1.100, port 54321. The STUN server processes the binding request and prepares a binding response. The server extracts the source IP address and port from the received packet, which is 198.51.100.10:62000, and includes this information in the response as the XOR mapped address attribute. The server also copies the transaction ID from the request into the response, ensuring the client can match this response to its original request. The response is then sent back to 198.51.100.10:62000. When the response packet arrives at the NAT device on its way back to the client, the NAT consults its translation table. It sees that external port 62000 maps to internal address 192.168.1.100:54321, so it translates the destination address and forwards the packet to the client. The client receives the STUN response, verifies the transaction ID matches its request, and extracts the XOR mapped address attribute. After performing the XOR operation to decode the address, the client now knows its public IP address and port, 198.51.100.10:62000. This information is invaluable for establishing peer-to-peer connections. The client can now advertise this public address to potential peers through a signaling mechanism like SIP or WebRTC signaling. When two peers exchange their respective reflexive addresses discovered through STUN, they can attempt to establish a direct connection by sending packets to each other's public addresses. This technique, known as hole punching, works because the NAT translation table entries are already established by the STUN exchanges, so packets arriving from the peer can be properly forwarded. TURN Protocol Fundamentals. While STUN enables direct peer-to-peer connections in many scenarios, there are situations where direct connectivity is simply impossible. This is where TURN, or Traversal Using Relays around NAT, becomes essential. TURN is defined in RFC 5766 and provides a relay mechanism that guarantees connectivity between peers, even in the most restrictive network environments. Unlike STUN, which is a lightweight protocol for address discovery, TURN is a full-featured relay protocol that actually handles the media traffic between peers. The fundamental difference between STUN and TURN is that STUN merely facilitates direct connections, while TURN actively relays data. When using STUN, if the connection succeeds, data flows directly between peers without touching the STUN server. With TURN, all data flows through the TURN server. The client sends data to the TURN server, which then forwards it to the destination peer, and vice versa. This makes TURN more resource-intensive for both the server operator and the network, but it provides guaranteed connectivity regardless of NAT or firewall restrictions. Turn operates through a concept called allocations. When a client connects to a turn server, it requests an allocation, which is essentially a relayed transport address. The turn server allocates a public IP address and port on behalf of the client and creates a binding between the client's actual address and this relayed address. This relayed address can be shared with peers, who can then send data to it. When data arrives at the relayed address, the turn server forwards it to the client that created the allocation. TURN supports multiple transport protocols. The communication between the client and the TURN server can occur over UDP, TCP, or TLS, depending on what the network allows. Similarly, the relayed traffic between the TURN server and peers can use UDP or TCP. This flexibility is crucial because some enterprise firewalls block UDP entirely, allowing only TCP traffic. TURN's ability to relay between different transport protocols, such as receiving data via TCP from a client and forwarding it via UDP to a peer, makes it extremely versatile. Authentication and security are critical aspects of TURN because TURN servers relay data and consume bandwidth. They are valuable resources that must be protected against abuse. TURN uses a short-term or long-term credential mechanism to authenticate clients. Short-term credentials are typically used in managed environments where a central authentication server can issue time-limited credentials. Long-term credentials use username and password authentication with message integrity protection. Without proper authentication, a TURN server could be abused for bandwidth amplification attacks or unauthorized relay services. TURN allocation process. The process of creating a TURN allocation is more complex than a simple STUN binding request because it involves authentication, authorization, and resource allocation. Let us walk through this process step by step to understand how a client obtains a relayed transport address from a TURN server. The journey begins when the client recognizes that direct peer-to-peer connectivity has failed, perhaps after attempting STUN-based hole punching and encountering symmetric NAT or restrictive firewalls. The client initiates the allocation process by sending an allocate request to the TURN server. This initial request does not include credentials because the client does not yet know what realm or nonce to use for authentication. The TURN server responds with a 401 unauthorized error response, which includes a REALM attribute indicating the authentication realm and a NONCE attribute containing a random value that must be used in subsequent authenticated requests. This challenge response mechanism prevents replay attacks and ensures that credentials are bound to a specific server session. Upon receiving the 401 error, the client prepares a new allocate request, this time including authentication credentials. The client computes a message integrity hash using the HMACSHA1 algorithm, combining the username, password, realm, and nonce with the message content. This hash is included in the message integrity attribute of the request. The client also specifies in the request what transport protocol it wants for the relayed address, typically UDP, and may include a requested transport attribute to indicate this preference. The TURN server receives this authenticated allocate request and validates the credentials. It checks that the username is authorized to create allocations, verifies the message integrity hash, and ensures the NONCE has not expired. If authentication succeeds, the server proceeds with resource allocation. The server selects an available IP address and port from its pool of relay addresses, creates internal state to track this allocation, and associates it with the client's actual source address. The server also starts a timer because TURN allocations have a limited lifetime, typically 10 minutes by default, though this can be refreshed. The turn server responds with an allocate success response containing several important attributes. The XOR relayed address attribute contains the relayed transport address that the server has allocated for the client. This is the public IP and port that peers can use to send data to the client. The lifetime attribute indicates how long the allocation will remain valid. The XOR mapped address attribute provides the client's reflexive address as seen by the turn server, similar to stun. The client can now use this relayed address for communication with peers, and it must periodically send refresh requests to keep the allocation alive. TURN permissions and channels. Creating an allocation on a TURN server is just the first step. For security reasons, the TURN server does not automatically relay traffic from just anyone to the client's relayed address. Instead, TURN implements a permission system that controls which peers can send data through the relay. This prevents unauthorized parties from using your allocation and helps protect against certain types of attacks where malicious actors might try to relay unwanted traffic through your allocation. Permissions in TURN are based on IP addresses, not port numbers. When a client wants to receive data from a specific peer through the TURN relay, it must first install a permission for that peer's IP address. This is done by sending a create permission request to the TURN server, including the peer's IP address in the XOR peer address attribute. The TURN server creates a permission entry that allows data from that IP address to be relayed to the client. Note that the permission is IP-based, so data from any port on that IP address will be accepted once the permission is installed. Permissions have a lifetime, typically 5 minutes, and must be refreshed periodically to remain valid. This timeout serves as a security measure, ensuring that permissions do not remain active indefinitely for peers that are no longer communicating. If a permission expires and data arrives from that peer's IP address, the TURN server silently drops the data rather than relaying it. The client is responsible for maintaining permissions for all active peers by sending periodic create permission requests to refresh them before expiration. While permissions control who can send data, TURN also provides an optimization mechanism called channels to reduce overhead. Without channels, all relayed data must be encapsulated in TURN send and data indications, which add significant header overhead. Each packet requires a TURN header, padding for alignment, and attribute encoding. For high-bandwidth applications like video streaming, this overhead becomes substantial and wasteful. Channels solve this problem by allowing the client to create a lightweight binding between a peer address and a channel number. Once a channel is bound, data to and from that peer can be sent using a minimal 4-byte channel data header instead of the full TURN send or data indication format. The client sends a channel bind request specifying the peer's IP address and port, and a channel number beginning with 0x ending with 00 and beginning with 0x ending with FF. Once bound, data destined for that peer is sent in channel data messages with just the channel number and length, dramatically reducing overhead. Channels also have lifetimes, typically 10 minutes, and must be refreshed to remain active. The channel binding mechanism makes TURN relay much more efficient for sustained media flows. ICE framework integration. While STUN and TURN are powerful protocols in their own right, they truly shine when integrated into the ICE framework. ICE stands for Interactive Connectivity Establishment, and it is defined in RFC 8445. ICE is not a separate protocol but rather a framework that systematically uses STUN and TURN to discover the best possible connectivity path between two peers. The genius of ICE is that it tries multiple connection strategies simultaneously and selects the one that works best, providing both optimal performance and guaranteed connectivity. ICE introduces the concept of candidates, which are potential addresses that can be used for communication. There are 3 types of candidates. Host candidates are the local IP addresses and ports on your device, such as your Wi-Fi or Ethernet interface address. Server reflexive candidates are public IP addresses and ports discovered through STUN, representing how your device appears after NAT translation. Relayed candidates are the addresses allocated through TURN servers, providing guaranteed connectivity through relay. The ICE process begins with candidate gathering. Each peer uses STUN to discover its server reflexive candidates and contacts TURN servers to obtain relayed candidates. The peer collects all of these candidates, including host, server reflexive, and relayed ones, into a list. This candidate list is then exchanged with the other peer through a signaling channel. The signaling channel is separate from the media path and typically uses a protocol like SIP, XMPP, or WebRTC signaling over WebSockets. Each peer shares its complete list of candidates with the other peer. Once both peers have received each other's candidate lists, they enter the connectivity check phase. This is where ICE performs its systematic testing. Each peer creates candidate pairs by pairing each of its own candidates with each of the remote peer's candidates. For example, if you have 3 local candidates and receive 3 remote candidates, you have 9 possible pairs. These pairs are prioritized based on candidate types, with direct connections preferred over relayed connections. The peers then perform connectivity checks by sending STUN binding requests to each candidate pair. The connectivity checks serve multiple purposes. First, they verify that a path exists between the candidate pair. Second, for candidates behind NAT, these checks perform hole punching, creating the necessary NAT bindings that allow bidirectional communication. Third, the checks measure the round-trip time, which helps determine which path offers the best performance. As checks succeed or fail, ICE updates its candidate pair priorities and eventually nominates the best working pair for media transmission. This entire process happens automatically and usually completes within seconds, seamlessly handling NAT Traversal without user intervention. Practical deployment considerations. Deploying STUN and TURN servers in production environments requires careful planning and consideration of several factors. While STUN servers are relatively lightweight and can be deployed with minimal resources, TURN servers are significantly more demanding because they relay actual media traffic. Understanding these requirements is crucial for building a reliable real-time communication infrastructure that can scale to support your user base while maintaining quality of service. STUN server deployment is straightforward because STUN servers are stateless and handle only control traffic. A single STUN server can easily support thousands of clients because each STUN transaction consists of just a few small packets. The server receives a binding request, examines the source address, and sends back a response. There is no long-lived connection, no state to maintain between requests, and minimal CPU usage. Many organizations run STUN servers on very modest hardware or share STUN server capacity across multiple services. You can even use public STUN servers like those provided by Google for non-critical applications, though having your own STUN servers gives you better control and reliability. TURN server deployment is far more complex and resource-intensive. Unlike STUN, TURN servers maintain state for each allocation, track permissions and channels, and relay all media traffic between clients. A single video call relayed through TURN might consume several megabits per second of bandwidth in both directions. If you have hundreds or thousands of simultaneous calls using TURN relay, the bandwidth requirements become enormous. This is why TURN servers need to be deployed on high-bandwidth infrastructure with robust network connectivity and adequate server resources. Capacity planning for TURN servers involves estimating how many concurrent allocations you need to support and the bandwidth per allocation. For voice calls, you might estimate 100 kilobits per second per direction, so 200 kilobits per second per allocation. For standard definition video, perhaps 1 megabit per second per direction or 2 megabits per second per allocation. For high-definition video, this could be 2 to 4 megabits per second per direction. Multiply these figures by the number of concurrent calls, add overhead for protocol encapsulation, and include a safety margin, and you will have your bandwidth requirements. CPU and memory requirements depend on the packet rate and number of allocations, but are generally less constraining than bandwidth. Geographic distribution is another important consideration. STUN and TURN servers should be deployed close to your users to minimize latency. If your users are globally distributed, deploying TURN servers in multiple regions ensures that relayed traffic does not traverse unnecessary distances. A call between two users in Asia should not relay through a TURN server in North America if you can avoid it. Many deployments use GeoDNS or Anycast routing to direct clients to the nearest TURN server automatically. You also need to consider redundancy and failover. TURN servers can fail or become overloaded, so having multiple TURN servers and the ability to failover to alternatives is essential for production reliability. Security and authentication mechanisms. Security is paramount when deploying STUN and TURN infrastructure because these servers are exposed to the public internet and can be targets for abuse. While STUN servers are relatively low risk due to their stateless nature and minimal resource consumption, TURN servers represent a more significant security concern. An improperly secured TURN server can be exploited for bandwidth amplification attacks, used as an open relay for malicious traffic, or abused to consume your bandwidth and server resources. Understanding and implementing proper security measures is not optional, it is a critical requirement for any production deployment. STUN servers generally do not require authentication because they only provide information about the client's reflexive address and do not relay any actual traffic. The worst that an attacker can do with a STUN server is query their own public IP address, which is not particularly useful for malicious purposes. However, some deployments choose to implement rate limiting on STUN servers to prevent abuse, where an attacker could try to overwhelm the server with requests. Rate limiting can be based on the source IP address, allowing a certain number of requests per second from each unique IP address. TURN servers absolutely must implement authentication because they relay traffic and consume significant resources. The TURN protocol specifies two authentication mechanisms: short-term credentials and long-term credentials. Long-term credentials use a simple username and password authentication scheme where the client proves knowledge of a shared secret. The password is never sent in clear text. Instead, it is used to compute an HMACSHA-1 hash of the message content, which is sent in the message integrity attribute. The server verifies this hash using its own copy of the password. Short-term credentials are more sophisticated and are commonly used in managed environments. In this model, a separate authentication server issues time-limited credentials to authenticated clients. These credentials consist of a username that encodes an expiration timestamp and a temporary password derived from a shared secret known only to the authentication server and TURN server. When a client requests TURN access, it first authenticates with the authentication server using whatever authentication mechanism is appropriate for your environment, such as OAuth 2 or session cookies. The authentication server then issues short-term TURN credentials valid for a specific duration, typically 24 hours. The short-term credential mechanism provides several security benefits. First, compromised credentials have limited validity, reducing the window of opportunity for abuse. Second, the TURN server does not need to store user passwords or maintain a user database, but it only needs to know the shared secret for validating credentials. Third, you can revoke access by having the authentication server stop issuing credentials to specific users without needing to reconfigure the TURN server. This separation of concerns makes the system more secure and easier to manage at scale. Additionally, many deployments implement IP-based access control, allowing TURN servers to restrict which IP ranges can even attempt to create allocations, adding another layer of defense against abuse. NAT type detection techniques. Understanding what type of NAT you are behind is crucial to determine whether direct peer-to-peer connectivity is possible, or whether you will need to rely on TURN relay. Different NAT types have dramatically different behaviors when it comes to allowing inbound traffic, and STUN provides mechanisms to detect these behaviors. This detection process is sometimes called NAT behavior discovery or NAT type classification, and it is an essential step in the ICE connectivity establishment process. The classic NAT type taxonomy comes from RFC 3489, though it has been somewhat refined in later specifications. The most permissive type is full cone NAT, sometimes called one-to-one NAT. In this configuration, once an internal address and port is mapped to an external address and port, any external host can send packets to that external address and port, and they will be forwarded to the internal host. This is ideal for peer-to-peer connectivity because once you have created a mapping by sending an STUN request, peers can reach you at that public address without any additional coordination. Address-restricted cone NAT adds a layer of security by filtering based on source IP address. The NAT still maintains a consistent external port mapping for your internal address and port. However, it only forwards inbound packets from external hosts that you have previously sent packets to. For example, if your internal address 192.168.1.100:5000 maps to external address 198.51.100.10:6000, and you send a packet to peer 203.0.113.50, then that peer can send packets back to 198.51.100.10:6000, and they will reach you. However, a different peer at 203.0.113.51 cannot reach you at that same external address until you have sent a packet to them first. Port-restricted cone NAT is even stricter. Not only must you have sent a packet to the external host's IP address, you must have sent a packet to that specific IP address and port combination. If you send to 203.0.113.50:8000, then only packets from exactly 203.0.113.50:8000 will be forwarded to you. Packets from 203.0.113.50:8001 would be blocked even though they are from the same IP address. This level of restriction makes peer-to-peer connectivity more challenging because both peers need to coordinate precisely which ports they are using. Symmetric NAT is the most restrictive type and the most problematic for peer-to-peer connectivity. Unlike cone NATs which maintain consistent external port mappings, symmetric NAT creates a different external port mapping for each destination you communicate with. If you send packets from internal port 5000 to destination A, you might get external port 6000. But if you send from the same internal port 5000 to destination B, you get a completely different external port, say 6100. This makes it nearly impossible to predict what external address a peer should use to reach you, because the address changes depending on where you're sending. Symmetric NAT essentially requires TURN relay for reliable connectivity. STUN provides a procedure for detecting NAT type through a series of tests. The basic approach involves sending STUN requests to multiple STUN servers at different IP addresses and comparing the reflexive addresses returned. If you get the same reflexive address from different STUN servers, you're likely behind cone NAT. If you get different reflexive addresses, you're behind symmetric NAT. The specification includes a decision tree of tests involving requests to different server IPs, requests to different server ports, and analysis of the patterns in the responses to classify the NAT type. While NAT type detection isn't perfect and can be complicated by multiple layers of NAT or unusual configurations, it provides valuable information for making connectivity decisions. TURN data relay mechanisms. Once a TURN allocation is established and permissions are set up, the actual process of relaying data through the TURN server can happen in two different ways: using send and data indications or using channel data messages. Understanding these two mechanisms and knowing when to use each is important for optimizing the performance of TURN relay. particularly for bandwidth-intensive applications like video conferencing where every byte of overhead matters. The send indication is used by the client to send data to a peer through the TURN server. When the client wants to send data to a peer, it encapsulates the data in a TURN send indication message. This message includes the XOR peer address attribute containing the peer's IP address and port, and the data attribute containing the actual payload to be relayed. The TURN server receives this send indication, extracts the peer address and data, and forwards the data to the specified peer as a normal UDP or TCP packet. The server doesn't forward the TURN message structure, just the raw data from the data attribute. In the reverse direction, when data arrives at the TURN server from a peer destined for a client's relayed address, the server encapsulates this data in a TURN data indication message. The data indication includes the X or peer address attribute identifying which peer sent the data, and the data attribute containing the payload. The server sends this data indication to the client that owns the allocation. The client receives the data indication, extracts the peer address to know who sent the data, and extracts the data payload for processing by the application. While send and data indications work reliably, they have significant overhead. A TURN message includes a 20-byte header, plus the attributes with their own type length value encoding. The XOR peer address attribute is 8 bytes for IPv4 or 20 bytes for IPv6. The data attribute has a 4-byte header plus the actual data payload, and then padding might be added to maintain 4-byte alignment. For small packets, this overhead can easily be 30 to 40 bytes per packet. When you're sending thousands of packets per second for real-time media, this overhead consumes substantial bandwidth. Channel data messages solve this overhead problem through a much more efficient encoding. Once a channel is bound to a peer address using the channel bind request, subsequent data to and from that peer can be sent using channel data messages. A channel data message has a minimal 4-byte header containing just the channel number and the length of the data. The data payload follows immediately with no additional attribute encoding or padding requirements. This reduces overhead from 30 to 40 bytes down to just 4 bytes, a dramatic improvement for high packet rate applications. The trade-off with channels is that they require setup and maintenance. Before using a channel, the client must send a channel bind request to associate the channel number with the peer's address. Channel bindings have a lifetime, typically 10 minutes, and must be refreshed by sending new channel bind requests before they expire. The client also needs to manage the mapping between channel numbers and peer addresses, ensuring it uses the correct channel number for each peer. Despite this added complexity, the bandwidth savings make channels essential for any sustained media streaming through TURN. Most implementations start with send/data indications for initial packets and quickly transition to channels once the connection is established and the peer addresses are stable. ICE Candidate Gathering Process. The ICE candidate gathering process is where STUN and TURN come together to collect all possible addresses that could be used for connectivity. This is a comprehensive discovery phase where the application systematically explores every potential path to the peer, from the most direct local connections to fully relayed TURN paths. Understanding how candidate gathering works helps explain why ICE is so effective at establishing connectivity across diverse network conditions. The gathering process starts with host candidates, which are the actual local IP addresses on the device. A typical device might have multiple network interfaces: a Wi-Fi adapter, an Ethernet adapter, perhaps a VPN interface. Each interface has its own IP address, and each represents a potential path for connectivity. The application enumerates all these interfaces and their addresses, creating a host candidate for each. These host candidates are given the highest priority because direct local connections offer the best performance with zero latency and no bandwidth consumption on external servers. Next comes the discovery of server reflexive candidates using STUN. The application sends STUN binding requests to one or more STUN servers. For each host candidate, the application typically sends a STUN request from that specific local address. The STUN server responds with the reflexive address, which is how that local address appears after NAT translation. This reflexive address becomes a server reflexive candidate. The application usually queries multiple STUN servers to ensure reliability and to potentially detect symmetric NAT by comparing whether the reflexive addresses are consistent across different server destinations. Server reflexive candidate gathering can be quite fast, usually completing within a few hundred milliseconds. The STUN requests are small, responses are quick, and STUN servers are generally responsive. However, the application needs to handle STUN failures gracefully. If a STUN server is unreachable or slow to respond, the application typically times out after a second or two and moves on. The goal is to gather candidates quickly rather than waiting indefinitely for unresponsive servers. Having multiple STUN servers configured provides redundancy against server failures. Finally, the application allocates relayed candidates through turn. This process takes longer than STUN because it involves authentication and resource allocation. The application sends allocate requests to configured turn servers, goes through the authentication challenge response cycle, and receives the relayed address if allocation succeeds. The relayed address becomes a relayed candidate. Because turn is more expensive in terms of latency and resources, relayed candidates are given the lowest priority. They serve as the fallback option when all else fails, but they guarantee that connectivity will succeed even in the most restrictive network environments. The entire gathering process happens in parallel as much as possible to minimize total time. The application doesn't wait for STUN to complete before starting TURN allocation. Instead, it initiates all the discovery operations simultaneously. As each candidate is discovered, it's added to the candidate list and potentially sent to the peer via the signaling channel. This parallel approach means that ICE gathering typically completes within 2 to 5 seconds, even though it's performing multiple network operations. Once gathering is complete, the application has a comprehensive list of every possible way to reach the peer, ready for connectivity checking. ICE connectivity checks and nomination. After both peers have gathered their candidates and exchanged them via signaling, ICE enters its most critical phase, connectivity checks. This is where ICE tests each candidate pair to determine which ones actually work and which provides the best performance. The connectivity check process is systematic and methodical, using STUN messages to probe each potential path and measure its characteristics. Understanding this process reveals how ICE manages to find working connectivity even in complex network scenarios. ICE creates candidate pairs by pairing each local candidate with each remote candidate received from the peer. If you have 3 local candidates and receive 4 remote candidates from the peer, you end up with 12 candidate pairs to test. These pairs are organized into a checklist and prioritized based on the candidate types involved. Pairs involving host candidates get highest priority because they represent direct connectivity. Pairs with server reflexive candidates get medium priority. Pairs with relayed candidates get lowest priority because they involve TURN relay. Within each priority level, pairs can be further ordered based on other factors like network interface preferences. The connectivity check itself is an STUN binding request sent from the local candidate to the remote candidate. But this is not just an ordinary STUN request. It includes special ICE attributes that provide additional information. The priority attribute indicates how much this peer prefers using this particular candidate. The use candidate attribute, in regular nomination, tells the peer that this candidate pair is being nominated for use. The ICE controlling and ICE controlled attributes help establish roles when both peers are performing checks simultaneously. The binding request also includes authentication credentials so the peer can verify the check is legitimate. What makes ICE connectivity checks powerful is that they serve multiple purposes at the same time. First, they verify that a bidirectional path exists between the candidate pair. Second, for candidates behind NAT, the checks perform hole punching by creating NAT bindings that allow the peer's responses to traverse back through the NAT. Third, the checks measure round-trip time by timing how long the response takes, providing performance data for selecting the best path. Fourth, the checks establish the binding needed for subsequent media flow through that path. This multi-purpose design makes ICE extremely efficient. As connectivity checks succeed, ICE maintains state about which pairs work and their measured latency. The peers exchange information about check results through their responses to binding requests. When a peer receives a binding request and determines the check succeeds, it sends back a binding response. This response tells the initiating peer that the path works. ICE also implements triggered checks, where receiving a connectivity check triggers sending a check in the reverse direction, ensuring bidirectional validation. Once ICE has discovered one or more working candidate pairs, it moves to the nomination phase. In regular nomination mode, one peer is designated the controlling agent and decides which candidate pair to nominate. The controlling peer sends a binding request with the USECANDIDATE flag set to its preferred pair. When the controlled peer receives this and the check succeeds, the pair becomes nominated. In aggressive nomination mode, checks include the USECANDIDATE flag from the start, speeding up the process. Once a pair is nominated and both peers agree, that pair becomes the selected candidate pair for media transmission, and media can start flowing. ICE typically completes this entire process within a few seconds, seamlessly establishing connectivity without user intervention. Symmetric NAT Traversal Challenges. Symmetric NAT presents the most significant challenge for direct peer-to-peer connectivity, and understanding why requires looking at the fundamental behavior that makes symmetric NAT different from other NAT types. The key problem is that symmetric NAT does not provide predictable port mappings. Every time you send to a different destination, you get a different external port, making it impossible for peers to know what address to use when trying to reach you. This behavior breaks the assumptions that techniques like hole punching rely on. Let's trace through a specific scenario to see where symmetric NAT causes problems. Suppose you're behind symmetric NAT with internal address 192.168.1.100:5000. You send a STUN request to STUN server at 203.0.113.5:3478. Your NAT assigns external port 6000 for this destination, so the STUN server sees your packet coming from 198.51.100.10:6000. The server responds telling you this reflexive address. You share this address with your peer through signaling, thinking the peer can reach you at 198.51.100.10:6000. But here's the problem. When your peer tries to send packets to 198.51.100.10 port 6000, those packets arrive at your NAT from the peer's IP address, which is completely different from the STUN server's address. Your symmetric NAT looks at its mapping table and sees that port 6000 was allocated specifically for traffic with destination 203.0.113.5 port 3478. Traffic from this different source address doesn't match that mapping, so the NAT drops the packets. The peer cannot reach you at the address you discovered through STUN because that address is only valid for talking to the STUN server. The situation gets even more complex when both peers are behind symmetric NAT. Each peer discovers a reflexive address through STUN, but those addresses only work for talking to the STUN servers, not for talking to each other. When peer A tries to reach peer B using B's STUN discovered address, it fails because that address isn't valid for traffic from A. Similarly, when B tries to reach A, it fails for the same reason. Even techniques like simultaneous open, where both sides send packets at the same time hoping to create reciprocal NAT bindings, often fail with symmetric NAT because the NAT creates new port mappings for each new destination. Some sophisticated techniques exist to work around symmetric NAT in certain scenarios, but they are not reliable. One approach is port prediction, where one attempts to guess what port the symmetric NAT will assign next based on patterns in previous port assignments. Some symmetric NATs increment ports sequentially, so if 6000 was allocated for one destination and 6001 for another, one might predict 6002 for the next. But this is unreliable and will fail if the NAT's port allocation algorithm is random or if there is any delay between allocations. Another approach is birthday paradox-based methods where both peers rapidly create many allocations hoping that by chance they will hit matching ports, but this is inefficient and not guaranteed to succeed. The reality is that symmetric NAT scenarios often require turn relay for reliable connectivity. This is exactly why turn exists as part of the ICE framework. ICE will attempt direct connectivity first, trying various techniques and candidate pairs. When these attempts fail, as they often do with symmetric NAT, ICE falls back to the relayed candidate obtained through turn. The turn server acts as a middleman, receiving traffic from both peers at their respective relayed addresses and forwarding between them. While this adds latency and consumes server resources, it provides guaranteed connectivity. This reliability is why enterprise WebRTC deployments always include turn servers, even though the majority of connections may succeed with direct or stun-assisted paths. TURN load balancing and scaling. Operating TURN infrastructure at scale requires careful attention to load balancing and capacity management. Unlike STUN servers, which are lightweight and easy to scale, TURN servers handle actual media traffic and can quickly become bottlenecks if not properly architected. A single, poorly planned TURN deployment can limit your entire real-time communication infrastructure, causing call quality issues and failures when servers become overloaded. Let's explore the strategies and considerations for building scalable TURN infrastructure. The first challenge is determining how many concurrent allocations a single turn server can handle. This depends heavily on the hardware specifications and the type of traffic being relayed. A turn server relaying audio calls consumes much less bandwidth per allocation than one relaying HD video. For planning purposes, you might estimate that an audio call uses about 100 kilobits per second bidirectional, while an HD video call uses 2 to 4 megabits per second bidirectional. If you have a server with 1 gigabits per second network capacity and you are primarily relaying video calls at 3 megabits per second per call, you can theoretically support about 333 concurrent calls. In practice, you want to provision more capacity to handle burst traffic and not run servers at 100% utilization. CPU and memory are also constraints, though typically less severe than bandwidth. TURN servers need CPU cycles to process STUN messages, manage allocations and permissions, and forward packets. Memory is needed to maintain state for each allocation, including the mapping between client addresses and relayed addresses, permission lists, and channel bindings. A well-optimized TURN implementation can handle thousands of concurrent allocations on modest hardware, but you need to test your specific TURN server software under load to understand its characteristics. Memory usage grows linearly with the number of allocations, while CPU usage depends more on packet rates. Load balancing across multiple TURN servers can be achieved through several mechanisms. The simplest approach is client-side load balancing through DNS. You configure multiple TURN servers with different hostnames or IP addresses and distribute them to clients through your ICE server configuration. Clients randomly select from the available servers when allocating. This works but has limitations. You can't control the distribution precisely, and if one server becomes overloaded, new clients might still select it until it starts failing. There's no dynamic feedback mechanism to avoid overloaded servers. A more sophisticated approach uses a dedicated load balancer in front of your TURN servers. However, this is tricky because TURN is a stateful protocol. You can't simply round-robin requests to different backend servers. This is because a client's allocation resides on a specific server, and all subsequent requests for that allocation must reach that same server. You need session persistence, often called sticky sessions, where the load balancer consistently routes all traffic from a given client to the same backend TURN server. This can be implemented based on client IP address or by parsing TURN messages to extract the transaction ID or allocation identifier. Geographic distribution is crucial for minimizing latency in turn relay. If two users in Tokyo are communicating, but their turn relay is in London, their media is taking an unnecessary round trip to Europe and back. Deploying turn servers in multiple regions and using GeoDNS to direct clients to nearby servers significantly improves performance. You might have turn clusters in North America, Europe, Asia, and South America, with clients automatically directed to the nearest cluster based on their location. This geographic strategy also provides resilience against regional failures or connectivity issues affecting specific regions. Monitoring and alerting are essential for production TURN deployments. You need to track key metrics including active allocations, bandwidth consumption, packet rates, success and error rates for allocate requests, and server resource utilization. Setting up alerts when servers approach capacity thresholds gives you warning to scale up before users experience problems. Many deployments implement automatic scaling where new TURN servers are provisioned when existing servers reach 70 to 80% capacity and decommissioned when utilization drops. This elastic scaling helps manage costs while ensuring adequate capacity for peak usage periods. Protocol security vulnerabilities. While stun and turn have been designed with security considerations, like any network protocol, they have potential vulnerabilities that must be understood and mitigated. Operating these services on the public internet exposes them to various attack vectors, from simple denial of service attempts to more sophisticated amplification and relay abuse. Understanding these vulnerabilities helps operators implement appropriate defensive measures and helps developers build more resilient applications. STUN amplification attacks exploit the fact that STUN responses can be larger than requests. An attacker sends a small STUN request with a spoofed source IP address, making it appear to come from the victim's address. The STUN server, seeing what it believes is a legitimate request from the victim, sends its response to the victim. If the response is larger than the request, the attacker has amplified their traffic. While STUN's amplification factor is relatively low compared to protocols like DNS or NTP, it can still be used as part of a distributed denial of service attack. Mitigation includes rate limiting based on source IP addresses and implementing response rate limiting to prevent the server from being used as an amplification vector. Turn servers face more serious security risks due to their relay functionality. An open turn server without proper authentication can be abused as a proxy for malicious traffic. An attacker could use your turn server to relay attacks against third parties, making it appear the attacks originate from your infrastructure. This could result in your IP addresses being blacklisted or your service being used in illegal activities. This is why authentication is absolutely mandatory for turn servers in production. Never operate a turn server that allows anonymous allocations unless it is in a completely controlled environment like a private test network. Even with authentication, turn servers can be targets for resource exhaustion attacks. An attacker with valid credentials could create many allocations and leave them open without using them, consuming server resources and preventing legitimate users from obtaining allocations. Or they could create allocations and send massive amounts of data through them, exhausting server bandwidth. Defense requires implementing quotas and limits per user or per source IP address. Limit the number of concurrent allocations per user. Set bandwidth limits per allocation, and implement idle timeouts that deallocate unused allocations. Monitor for abnormal usage patterns that might indicate abuse. The authentication mechanisms themselves can be vulnerable if not properly implemented. Long-term credentials using static passwords are vulnerable to credential theft and replay attacks. If credentials are transmitted insecurely or stored improperly, they can be compromised. Short-term credentials with limited validity are more secure, but the credential issuance process must be protected. Ensure that your authentication server uses HTTPS when issuing credentials to clients, and implement proper password hashing with SALT if storing long-term credentials in a database. The TURN protocol's message integrity mechanism provides protection against tampering, but it doesn't encrypt the data being relayed. Privacy is another consideration, particularly for STUN. When you send a STUN request, you reveal your IP address to the STUN server. If you are concerned about privacy, this is a leak of information about your network location. TURN Relay can actually enhance privacy by hiding your real IP address from peers, since peers only see the TURN server's address, not yours. However, the TURN server itself sees all the traffic passing through it. If you are relaying sensitive communications, the TURN server operator could potentially intercept or log that traffic. This is why many secure applications use end-to-end encryption at the application layer, encrypting media before sending it through TURN, so the TURN server only sees encrypted data. DTLS-SRTP in WebRTC provides this protection, ensuring that even if traffic passes through TURN, the actual media content remains encrypted and inaccessible to the relay server. WebRTC Integration Architecture. WebRTC, or Web Real-Time Communication, is the most prominent user of STUN and TURN protocols in modern applications. Understanding how WebRTC integrates these protocols provides insight into real-world deployment patterns and best practices. WebRTC is built into web browsers and provides JavaScript APIs that allow web applications to establish peer-to-peer audio, video, and data connections without plugins. Under the hood, WebRTC uses ICE for connectivity establishment, which in turn relies on STUN and TURN for NAT Traversal. A WebRTC application typically starts by creating a peer connection object in JavaScript. This object represents the connection to a remote peer and encapsulates all the complexity of media handling, codec negotiation, and connectivity establishment. When you create a peer connection, you provide an ICE configuration that specifies the STUN and TURN servers to use. This configuration is an array of server objects, each containing URLs for the servers and credentials if needed. For example, you might configure STUN servers using URLs like stun:/stun.example.com:3478 and TURN servers using turn:/turn.example.com:3478 with associated username and credential fields. The WebRTC implementation handles ICE candidate gathering automatically. As soon as you create the peer connection and start adding media tracks or data channels, the browser begins gathering candidates. It enumerates local network interfaces for host candidates, sends STUN requests to the configured STUN servers for server reflexive candidates, and initiates TURN allocations for relayed candidates. As each candidate is gathered, the browser fires an ICE candidate event containing the candidate information. Your application is responsible for sending these candidates to the remote peer through whatever signaling mechanism you have implemented. Signaling in WebRTC is deliberately not specified by the standard, giving developers flexibility to use whatever signaling protocol fits their application. You might use WebSockets, HTTP polling, SIP, XMPP, or any other message transport. The signaling channel needs to convey three types of information: session descriptions using SDP, which describe media capabilities and parameters, ICE candidates discovered during gathering, and control messages for call setup and teardown. The signaling channel doesn't carry media, only control information. The actual media flows peer-to-peer using the path established through ICE. Once candidates are exchanged and connectivity checks complete, WebRTC establishes the media connection using DTLS for key exchange and SRTP for media encryption. This happens automatically without application intervention. If the ICE process selected a direct or STUN-assisted path, media flows directly between peers with end-to-end encryption. If the selected path uses TURN relay, media flows through the TURN server, but remains encrypted end-to-end. The TURN server cannot decrypt the media because the DTLS SRTP keys are negotiated between the peers, not shared with the TURN server. This provides privacy even when using relay. WebRTC applications need to handle ICE failures and connection state changes. The peer connection object fires events like ICE connection state change and connection state change that indicate the current connectivity status. States include new, checking, connected, completed, failed, disconnected, and closed. Your application should monitor these states and handle failures appropriately, perhaps by notifying the user that the connection failed or attempting to restart ICE with different server configurations. Connection quality can also be monitored using WebRTC statistics APIs, which provide detailed metrics about packet loss, jitter, bandwidth, and other performance indicators. Production applications should collect and analyze these statistics to understand connectivity patterns and optimize their STUN and TURN server configurations. Troubleshooting connectivity issues. Despite ICE's robustness, connectivity issues still occur in production deployments. Knowing how to diagnose and resolve them is essential for maintaining reliable, real-time communication services. Troubleshooting requires understanding where in the connectivity establishment process things can go wrong, what logs and metrics to examine, and what tools can help identify the root cause. Let's walk through a systematic approach to diagnosing STUN and TURN-related connectivity problems. The first step in troubleshooting is to gather information about what is actually happening during ICE processing. Most WebRTC implementations and STUN/TURN client libraries provide detailed logging that can be enabled for debugging. In Chrome, you can navigate to chrome://WebRTC internals to see detailed information about all active peer connections, including ICE candidates gathered, connectivity checks performed, and the final selected candidate pair. Firefox has similar capabilities at about WebRTC. These browser debugging interfaces show you exactly what candidates were discovered, which checks succeeded or failed, and any errors that occurred. One common issue is failure to gather server reflexive candidates, indicating that STUN is not working. This could be due to network firewalls blocking UDP traffic to the STUN server, incorrect STUN server addresses in the configuration, or STUN servers being down or unreachable. You can test STUN connectivity independently using command line tools like StunServer or online STUN testing websites. If STUN requests timeout, check that UDP port 3478 is allowed through any firewalls, and that DNS resolution for the STUN server hostname works correctly. Some networks block UDP entirely, which would prevent STUN from functioning over UDP and require TURN over TCP as a fallback. TURN allocation failures are another frequent issue. The most common cause is authentication problems. Check that the credentials provided to the client match what the TURN server expects. With short-term credentials, ensure the credential hasn't expired, which can happen if there's significant clock skew between the authentication server and the client. Verify that the credential format is correct, including the proper username encoding that includes the expiration timestamp for time-limited credentials. Authentication errors usually appear in TURN server logs, so checking server-side logs is valuable for diagnosing credential issues. Sometimes allocations succeed, but connectivity checks still fail. This could indicate that the turn server is allocating an address that's not actually reachable, perhaps due to incorrect network configuration or firewall rules. Verify that the relayed addresses being allocated are publicly routable and that the turn server has proper routing configured to reach clients. You can test turn connectivity using tools like Turn Utils uClient, which performs allocation and sends test data through the relay. If test tools work but your application doesn't, the issue might be in how your application is using the turn allocation rather than with the turn server itself. Network path MTU issues can cause subtle problems where connectivity works initially but then fails when larger packets are sent. If TURN is operating over UDP and the path MTU between the client and TURN server is smaller than expected, packets might be fragmented or dropped. This is more common in environments with VPNs or tunneling protocols that reduce effective MTU. Using TURN over TCP can work around UDP MTU issues, though at the cost of higher latency. Monitoring packet loss rates in WebRTC statistics can reveal path quality problems. For systematic debugging, implement comprehensive logging in your application that records ICE states, gathered candidates, connectivity check results, and final selected paths. Log this information to a centralized logging system where you can analyze patterns across many sessions. Look for trends like high failure rates with specific TURN servers, indicating server issues, or failures concentrated in specific geographic regions, suggesting network problems in those areas. Build dashboards that visualize key metrics like ICE success rate, time to connectivity, percentage of connections using TURN versus direct paths, and TURN server utilization. These metrics help you proactively identify and address issues before they impact users significantly. Future evolution and alternatives. As the Internet evolves, so too do the protocols and techniques for establishing connectivity. While STUN and TURN have served the real-time communication community well for over a decade, newer approaches and protocol enhancements are emerging that address some of their limitations and better fit modern network architectures. Understanding these developments helps inform future-looking infrastructure decisions and provides context for how NAT Traversal might work in coming years. The most significant future change will come from IPv6 adoption. IPv6 was designed to eliminate the need for NAT by providing enough addresses for every device on Earth to have unique public addresses. In a pure IPv6 world, there is no NAT, which means no NAT traversal problem to solve. Devices can communicate directly using their globally routable IPv6 addresses. However, IPv6 adoption has been slower than many expected, and we are still in a dual-stack world where both IPv4 and IPv6 coexist. NAT64 and other transition mechanisms sometimes introduce new forms of address translation even in IPv6 networks. It will likely be many years before IPv6 is ubiquitous enough that we can completely abandon NAT traversal techniques. WebRTC has driven improvements to ICE through newer RFC specifications. RFC 8445 updated the original ICE specification with lessons learned from deployment experience. It introduced more efficient nomination procedures, better handling of ICE restarts when connectivity is lost, and refinements to how consent for sending data is maintained. Trickle ICE, which allows candidates to be sent to the peer as they are gathered rather than waiting for complete gathering, speeds up connection establishment. Incremental provisioning allows adding new TURN servers or adjusting ICE parameters mid-session without restarting the entire connection. QUIC, the transport protocol underlying HTTP/3, has interesting implications for NAT Traversal. QUIC operates over UDP but includes built-in encryption, congestion control, and connection migration capabilities. Connection migration allows a QUIC connection to survive IP address changes, which is valuable for mobile devices that might switch between Wi-Fi and cellular networks. While QUIC doesn't eliminate the need for NAT Traversal, its use of UDP and built-in encryption makes it more compatible with NAT traversal techniques, and its connection migration features could potentially reduce reliance on TURN in some mobile scenarios. Some researchers have explored alternatives to the STUN/TURN model. Port Control Protocol, or PCP, defined in RFC 6887, allows clients to request port mappings from NAT devices directly rather than relying on external servers to discover reflexive addresses. If NAT devices widely supported PCP, clients could create the mappings they need without STUN. However, PCP adoption has been limited, and many NAT devices do not implement it. NAT PMP, its predecessor, also saw limited deployment outside Apple's ecosystem. The challenge is that NAT traversal protocols require cooperation from NAT device manufacturers, and getting broad support is difficult. Looking forward, we might see application layer techniques become more sophisticated. Machine learning could potentially predict network topology and NAT behavior based on historical patterns, allowing applications to more quickly determine the likely best connectivity approach without exhaustively testing all candidates. Improved coordination between endpoints and network infrastructure through protocols like STIR/SHAKEN for telephony or emerging standards for network-assisted WebRTC could provide applications with better information about network conditions. Cloud-based relay networks might become more efficient through edge computing deployments that place relay servers closer to users, reducing relay latency. Thank you for your attendance. Please consider subscribing to the channel.